So this last section is all about what are called counting techniques. There are ways that we can very quickly choose different sets of people, which eventually does come into play in statistics and probability, but today we're just kind of focusing on these different counting techniques. What I've done is kind of made you a formula chart here at the front, so all of the formulas we're going to use are right here at the front. So when I'm referring to them, this is what I'm talking about with their description. But we're going to just jump right into examples because it's kind of important. Oh, by the way, this symbol, mathematically, if you didn't actually know this, the exclamation point is actually a mathematical symbol. It's called the factorial. And what it does is it means to multiply every number smaller than that number all the way to 1, multiply them together. So if we were doing 3 factorial, that would be 3 times 2 times 1. 5 factorial is 5 times 4 times 3 times 2 times 1. That's what a factorial is. It's a large, very quickly multiplying number. Fun fact though, all of this stuff can be done in the calculator and in Excel. So if you got really sturdy about using Excel, these are the following ways to do it. So again, I will come back to these steps throughout the lesson, but you're on the home screen, you're pressing math and then going over to the probability menu, PRB, and I think on the new calculators it actually says prob, P-R-O-B. Yes. And then you're selecting either option 4 for the factorial, option 2 or option 3 for our permutations and combinations when we get there, then going back to the home screen and evaluating the number. And then it has there the instructions for Excel if you so desired. But we'll go straight to the examples and just see how to use them. Example 1 asks us to figure out how many different meals can be ordered at this particular restaurant. The appetizers that you have option-wise are a soup or a salad. Your entree can be either baked chicken, a beef patty, beef liver, or a au jus. And then your dessert can be ice cream or cheesecake. So how many different combinations can we make here? How many different meals can we order? A lot. Here's how we figure this out. This is tapping into what's called the multiplication rule of counting. If a task requires a sequence of choices in which there are P selections for the first and Q selections for the second, R selections for the third, and so on, then the task of making these selections can be done in the following way. We're going to choose an appetizer, we're going to choose an entree, we're going to choose a dessert. So this is my appetizer, this is my entree, this is my dessert. How many options do I have for appetizer? 2. How many options do I have for entree? Entree has 2 E's at the end of it, Miss Quigley. 4. How many options do I have for dessert? If I multiply all those numbers together, 2 times 4 times 2, we have 16 different options for meals we can combine together. So y'all remember when we did like simple random sampling and I had you list out all of the like combinations of groups of 3 and it took like a whole piece of paper? The number of combinations that you could make was made up with this. This is how we were counting to see how many options we would have. Some other classic examples we have of counting like this is airport codes. This is when repetition of the object is allowed. So the International Air Transport Association assigns 3-letter codes to represent airport locations. For example, do y'all know the airport location for the airports here? DFW and, do y'all know what Love Fields is? Oh, yeah. No. DAL. Both 3-letter combinations. So DFW and DAL are the 3-letter combinations that represent the airports in our city. Okay, so this is a real thing. For example, Fort Lauderdale International Airport is FLL. How many different airport codes are possible? We want to choose 3 letters. So here's the first letter, here's the second letter, here's the third letter. We can repeat the letters each time because FLL repeated an L, or they could all be individual. So for my first letter, how many choices do I have? Oh, there are 26 letters in the alphabet, yes. For the second letter, how many choices do I have? 26. And for the third letter, how many choices do I have? 26. So if we do 26 times 26 times 26, yes, that's 26 cubed, which may be easier to type in. How many different airport codes can we make? 17,576. We can very quickly make a whole lot of options for the number of combinations of letters when we have 26 options and 3 choices. But let's say we cannot use repetition. So if perhaps we were doing airport codes, but you couldn't repeat a letter, the problem changes a little bit. It says in example 3, 3 members from a 14-member committee are to be randomly selected to serve as chair, vice chair, and secretary. The first person selected is the chair, the second one is the vice chair, and the third is the secretary. How many different committee structures are possible? Okay, so we have to choose 3 people. 1, 2, 3. We have the chair, we have the vice chair, and we have the secretary. How many choices do I have for the chair? 14. How many choices do I have for vice chair? 13, because I've already picked one. How many choices do I have for secretary? 12. So this time I didn't replace the names back in the hat when I was drawing them out. So how many different combinations of this committee structure do we have? 2,184 options out of this 14-person committee when we're picking 3 of them. Last example before we get a little shortcut here for us. You've just been hired as a book representative for Pearson Education. That's who writes your textbook. On your first day, you must travel to 7 schools to introduce yourself. How many different routes are possible? Okay. So the first time you stop at a school, how many options do you have to choose from? You're like, you got to visit 7 schools. So how many options do you have? 7. And then you go to visit the second school. How many options do you have? And then, okay, we see what's happening for, why did I almost write 6? 3, 2, 1. Whoa. Kind of already introduced this. What do you notice that I'm multiplying together? It goes from 7 all the way down to 1. This is actually an example of a factorial. This is 7 factorial. So instead of on your calculator doing 7 times 6 times 5 times 4 times 3 times 2 times 1, which is not that bad when it's 7, but imagine that number was 51. Yeah. We're going to type 7 on the home screen of our calculator. You're going to go to Math, over to the Probability menu, and option 4 is the Factorial button. It should type the exclamation point behind the 7, then you press Enter, and you get 7 factorial. And what is 7 factorial? 5,040. So there are 5,040 different routes you could take from school to school. Obviously, some of them wouldn't make sense. You would probably go in a particular order distance-wise, but that's how many different combinations you could make. Now, a permutation is a nice example of when these different things come into play. And we've actually already seen an example of a permutation here when order matters. So we're going to first compute these permutations by hand so you can see why it's super helpful to have a button for this on your calculator and what this button is doing. But if we are evaluating the permutation 7 permute 5, which is also sometimes called 7 choose 5, but choose will be a C, that's a combination. We're permutating, or we're choosing different ones in a particular order. The formula for 7 permute 5, 7P5, if I look at the front of my page to the formula chart, which again is all there for you, tells you to do the first number factorial divided by the first number minus the second number factorial. Obviously, I know you already know where the factorial button is, but stick with me mathematically so we can see what's happening here. This is 7 times 6 times 5 times 4 times 3 times 2 times 1. What would be the bottom? First of all, what's 7 minus 5? 2. And if I'm writing 2 factorial, isn't that just 2 times 1? Which means these things will cancel each other out. So we have 7 spaces, 7 options, and we're filling 5 of those spaces. Just like we did before, didn't the first time I picked something I have 7 choices, and then 6, and then 5, and then 4, and then 3? Well, I picked 5 people. This formula right here is doing exactly what we did on like that 3-person committee. That was 14 choose 3. Mathematically, this works out. But what's nice is that you don't have to go through all of these loops to get here. There is a permutation key on your calculator. On your calculator right now, type 7. Then press math and go over the probability menu. I think it's option 3. It's option 2. It puts a P on your home screen, yes?
Yes.
It's ready for you to type the next number. So you type a 5, you press enter. What do you get? 2,520, which is exactly what we would get if we multiply 7 times 6 times 5 times 4 times 3. Not times 2 times 1, because we've already crossed that out. Okay, by hand and then with the calculator so we can see what we're doing here. 5 permute 5 tells me to do the following. The first number factorial over the first number minus the second number factorial. Let's write this out. So 5 factorial would be 5 times 4 times 3 times 2 times 1. And what's 5 minus 5? 0. 0 factorial is 1. Just a fun fact. So these 1s are going to cancel each other out, which doesn't really do anything for this problem. 5 choose 5 means I have 5 spaces that I'm filling with 5 people. 5 times 4 times 3 times 2, which would be the same as 5. Math, probability, option 2, 5. What do you get?
120.
120. So there's 120 options for us to take 5 people and choose all 5 of them in a particular order. So if we go back to the kind of examples we were seeing earlier, except now that we have this ability to do permutations, we can do problems like number 6 a lot faster. In how many ways can horses in a 10-horse race finish first, second, and third? So order matters here. Finishing first is better than second and third, so the order in which we pick them is important. The ways that a 10-horse race could finish in the first 3 spots is 10, pick 3. Mathematically, again, I know that there's a button for this, but this would be 10 factorial over 10 minus 3 factorial. And I'm going to write this a particular way on purpose. This is going to be 10 times 9 times 8 times 7 factorial over 7 factorial. 10 minus 3 is 7. The 7 times 5 times 4 times 3 times 2 times 1 would all cancel because we have 7 factorial on top and bottom. 10 times 9 times 8 in my calculator would be 720. This is what we would have gotten if I had said choose the first horse, the second horse, and the third horse. You would have told me we have 10 choices, then 9 choices, then 8 choices, and you would have gotten 720. So when the numbers are smaller, it's honestly pretty easy just to think about this like the old way where you just give yourself spaces to choose them. But when the numbers get bigger or we're choosing lots of things, actually doing that permutation with the calculator might be significantly faster. So this one, again, you do 10, math, probability, option 2, type in 3, press enter, you get 720. Now that is a permutation. These examples, the order in which I picked them mattered because it was vice chair, it was chair, then vice chair, then secretary. It was first place, second place, then third place. But what if the order doesn't matter? If the order doesn't matter, then that's called a combination as opposed to a permutation. And all these definitions, by the way, I'm saying them out loud. They're on that front page. It talks on the front page about order mattering or order not mattering. In a combination, order doesn't matter. It says Roger, Ken, Tom, and Jay are going to play golf. Bless you. They will randomly select teams of 2 players each. List all possible team combinations. That is, list all the combinations of the 4 people, Roger, Ken, Tom, and Jay, taken 2 at a time. So let's just first do this by hand because we're really trying to make sure we understand what's happening. If we have our sample set here, our sample space, we could choose Roger and Ken, or Roger and Tom, or Roger and Jay. Right? That's that's 2 people. Who else could I pick? How about Ken and Tom? Who else could go with Ken? Ken and Jay. Now, why does it not matter that I could put like Ken and Roger? Does the order in which I pick this team matter? No, it's not like we're saying who's teeing first, who's teeing second. We're just saying who's paired up together. The order in which I list them doesn't matter, so it doesn't, like RJ and JR are not different. They're just a team. So after Ken and Jay, the last combination I can have is Tom and Jay. These are the different combinations of two people out of this list that could play golf. How many combinations are in this list? 6. So if I have 4 people and I'm choosing 2, that means I have a total of 6. This is different than when we do permutations. Permutations, the order matters. Combinations, the order does not matter. So I've introduced a new symbol for you. This looks like what we did for permutations, correct? But there's a C in the middle. So our formula is different. It's from the front of your page. But let's go over this formula so you can see what's happening. The formula for 4 choose 1 will be the first number factorial, this over the second number factorial multiplied by the first minus the second factorial. So mathematically, what's happening? If we multiply all this out, this is 4 times 3 times 2 times 1. The denominator, I would have 1 factorial, which is just 1. And then 4 minus 1, which is 3. So then I need 3 factorial. What cancels on top and bottom? 3, 2, 1. So 4 choose 1 is 4. Now that makes sense. I have 4 options in front of you. Pick one. How many ways can you pick one thing? 4 different ways. You could pick one of the 4 things. This makes sense. What if I present to you 6 things and I tell you choose 4? Mathematically, this would go 6 choose 4 would be the first thing factorial divided by the second thing factorial multiplied by first minus second factorial. Let's just see mathematically what's happening. This numerator is 6 times 5 times 4 times 3 times 2 times 1. The first part of the denominator would be 4 times 3 times 2 times 1. 6 minus 4 is 2. So 2 factorial is 2 times 1. What cancels out here? 4, 3, 2, 1, and just one of the 4, 3, and one of the 2s and the 1s. So if I rewrite this, because now I've got a lot going on here, I would have 6 times 5 over 2 times 1. 6 times 5 is 30. 2 times 1 is 2. Yep, that's 15. So if I presented you 6 things and I said choose 4 of them, you'd have 15 different ways you could choose 4 of them. The order in which you pick them does not matter. But of course, a fast way to do this is with the calculator. So let's just verify we know how to do this. You'll type the first number, 4. You'll go math probability, but this time you're choosing option 3, which is your combination instead of your permutation. Choose 1, you should get 4, and then do the same thing for the second one. Just verify you know how to use the calculator for this. Example 9 says, how many different simple random samples, statistics, chapter 1, of size 4 can be obtained from a population whose size is 20? So this is like on that 1.46, whichever one, homework that I gave you where I had you pick those books and you had to write out every single one. How many would you have had to write out if that sample size was 20 and you were picking 4 of them? Let's figure it out. So the sample size is 20. That's the full number you're choosing out of. And we're choosing 4. 20, choose 4. Does the order in which I choose them matter? Nope. No, because it's just a list of books or a list of, it doesn't say what we're doing. Simple random sample. Let's use our calculator for this one because 20 and 4, that'd be a lot of numbers I'm writing down to do 20 factorial, and I just am not about it. What did you get when you did 20 choose 4?
48, 45.
Yeah, imagine writing out all 4,845 options there. I know, that's why I didn't give you such a big sample size when we did this. I think I did 9 choose 3.
Yeah.
Still a lot.
But still.
Okay, so far we have looked at just straight up counting techniques. We have looked at permutations. We have looked at combinations. Permutations are when order matters. Combinations are when order does not matter. Our last 2 examples are called permutations with non-distinct items, and we're going to write that down because it'll help you figure out what part of our formula chart we're on. This is permutations with non-distinct items. All before this, we'd been using distinct items, meaning everything on my list was different. But in the next couple examples, we're going to be doing permutations, but like we might have like 3 red flags and 4 blue flags. So we have non-distinct items at play. And so it's a different formula entirely. Example 10 says the DNA sequence consists of letters representing a DNA strand that spells out the genetic code. There are 4 possible letters, A, C, G, and T. All my science people, can you help me out? This is a legitimate question because I don't remember. Oh, no, it's written there. What are the 4 names for these A, C, G, and T? Great. I honestly forgot how to pronounce all of those, so thank you so much for pronouncing them for me. Same, okay. Each representing a specific nucleotide base in the DNA strand. How many distinguishable How many distinguishable sequences can be formed using 2 A's, 2 C's, 3 G's, and 1 T? So the order in which we're doing these matter because the order in which they are changes the genetic code, which means to me we're doing a permutation. But since I have multiple A's and multiple C's and multiple G's, and then the 1 T, our formula for this permutation is not the one we just beep, beep, beep in our calculator. We're going to have to do them separately. So we can do the following. Here's how I personally do these. It's different than the formula that's in your formula chart. I will still show you how to use that formula, but to me, solving this problem works like this. Here are the A's that I have, here are the C's, here are the G's, and here are the T's. We're going to individually choose those spaces. Meaning, I'm going to do 8, choose 2. Why 8, by the way? What's 2 plus 2 plus 3 plus 1? 8. So I'm having 8. I'm choosing 2 of those to be A's. But then I've chosen those. So how many do I have left here?
7.
Wait, I've chosen 2?
Oh.
6. And then I'm choosing how many C's? 2. How many do I have left? 4. And how many G's am I choosing? 3. So how many do I have left for the T? 1, choose 1, which will be 1. Okay, let's individually do this. 8, choose 2 in your calculator is what? So we type 8, math, probability, option 3, type 2, press enter. How much is that? 28. For 6, choose 2. 15. For 4, choose 3. 4 ways. And then 1, choose 1. LOL, 1. So 28 times 15 times 4 times 1 is 1680. That's the total number of options when order matters for these different DNA sequences. The formula that was given to you on your formula chart, which comes from the fact that you do each of these chooses, is the following. We are going to do the total number, which you told me was 8. And we're going to divide that by the individual choices, which was 2 A's, 2 B's, 3 C's, and 1 T. 8 factorial divided by 2 factorial times 2 factorial times 3 factorial times 1 factorial. Do that in your calculator real fast, which is a lot of times hitting that factorial button, but this is good practice. Yeah, when you calculate this, we should get the same number. So this formula that we were given on the formula sheet here does make sense if we're choosing of the 8 to be A's, 2 of them, choosing 2 to be C's, choosing 3 to be G's, and choosing 1 to be T. This formula makes sense, and it works. And the formula, yes?
Does this work on the calculator on your phone?
That is a great question. Can I see yours, actually? Oh, what am I doing? I have it on. So yes, it does work on the one that you have on your phones. So the probability screen is just 2 clicks to the right, PRB, on that device. So let's get to this last example. Here's another example of arranging things that are non-distinct. So the order in which we are hanging these flags, the vertical arrangement, so in case you're like, what does that even mean? Basically what we do is take a flagpole and we're like putting the flags up, right? So let's say some of them are white, some of them are blue, and some of them are red. I know that's pink, but just you get it, okay? We're trying to see how many different orders of these flags can we put up. So that is a permutation, the order, of things that are the same, non-distinct items. So to answer this question, we would take the total number of options. What is the total number of flags here? 10. We're going to do 10 factorial. And we're going to divide it by the individual options for each color. How many white flags do we have? How many blue flags? And how many red flags? If we do 10 factorial divided by 5 factorial divided by, time 3 factorial, time 2 factorial, which, yes, is that factorial button a whole bunch of times, you will get the number of arrangements for these 10 flags. I know, it's a bunch of buttons. What'd you guys get? 2,520. Which is a lot of different combinations for these 10 objects. So the main idea, if you think back to the front page of this, we had all of those formulas that we can use. Okay, sorry, I had to copy paste the page to come back on this video. Okay, so again, I have all these formulas here, and this is what we used. When we were just doing like the ordering your dinner, we talked about the rule of counting. Then once we got to count the same object over and over again, we started to see that we might be either permuting, which is without replacement, or combining, which is when repetition is allowed and the order does not matter. This is where it's very important. So actually on your front page, I want you to highlight the following with me. For combinations, order does not matter. That's going to be the biggest thing, is that sometimes you'll try to do a combination when it's a permutation. And for permutations, I want you to highlight order matters. That's going to change which one you choose. And then that very last one, permutation. So again, order matters, but you have multiple of the same kind. So it's non-distinct items without putting them back. I would make sure you fully understand, 1, how to type these sorts of numbers into the calculator, and 2, when to use a combination versus a permutation.